Let's talk about the algorithm known as Conway's Game of Life. This is probably the most famous algorithm for cellular automata ever made, and it has a little bit of very interesting historical factors to it. John Conway, who unfortunately left us in 2021, I believe, due to problems associated with COVID, was a British scientist who developed in the 1970s this algorithm, inspired in part in what he saw in nature with the dynamic of the populations, right? Some individuals in the population die by overpopulation, underpopulation, and some others are born. This implementation of cellular automata is based on a grid. Each tile where we're going to be focusing on has 8 different neighbors at any time. Even those that are in the edges of the board are going to have as their companions the elements in the other side of the screen. We're going to use a concept that we have already seen before during the implementation of Langton's End that is called the flat torus. So here we are going to assume that every single tile has 8 neighbors in total. We have all of these 8 different neighbors. Now, the tile is going to be alive or dead. If the color is white, it is alive, and if the color is black, it is dead. The rules of the game of life are simple. If the tile is alive, with the color white, and it has less than 2 or more than 3 neighbors that are also white, this tile dies in the next generation due to overpopulation or underpopulation. So let's look at this example right here. We have 4 neighbors, which is more than the 3 that the tile requires to stay in the current state. Something very important, however, is that we do not modify the state of this tile during this iteration, because the information that it carries has to stay static until we finish traversing the entire 2-dimensional grid. Otherwise, we're going to encounter errors like populating the entire screen in black tiles with only one iteration of the grid. So this tile right here will die in the next generation due to overpopulation. In this other example, we have an environment that is just right. We have 3 neighbors that are alive, and the tile therefore stays alive in the next generation. Notice how here it almost seems like we should have an else statement. But because this else statement means doing nothing, we simply ignore it. So what happens if the tile is not alive, but instead it is dead? If this tile is dead, there is only one condition that can't produce a white tile in the next generation, and that is having exactly 3 neighbors that are alive. Any deviation from this number will result in the tile keeping its state as dead. We call this birth. Let's see if we can implement this using Python.